In this recitation, we'll be going over reinforcement learning, and this is just going to be a brief overview, so check out the references at the end if you want to learn more. So reinforcement learning has had many successes in the recent years. It has applications in robotics, finance, and games. Personally, my favorite example is AlphaZero and its ability to quickly master board games such as chess. And what's notable is that it searches far fewer positions than the previous best chess engines such as Stockfish, but it's much better. Google has also had success in using reinforcement learning to teach agents to play Atari games. An important concept in reinforcement learning is the interaction between the agent and the environment. So we can think of the agent as the one who acts upon the environment, and the environment responds to these actions. So at each time step t, the agent sees an observation OT and reward RT and takes action AT. The environment responds to this action and emits observation OT plus 1 and reward T plus 1. So an important environment model is the Markov decision process. Most problems in reinforcement learning can be modeled by an MDP. So there are 5 elements in an MDP: the set of states, set of actions, the transition probability function, and the reward function, and finally the discount factor. The reason this is called a Markov decision process is because it follows a Markov property where the future is independent of the past given the present. And you can see this in the transition probability function. Instead of conditioning on S of t and the S of t minus 1 and the S of t minus 2 and so on, we can just condition on S of t. This allows us to write the transition probability function as a matrix. So now we're going to consider the example on the right hand side, and we're going to go over each of these 5 elements. First, a set of finite states. In the example on the right, we can see there were 14 states and a terminal state. You might ask, there are 2 grayed out boxes, so aren't there 2 terminal states? Well, usually we just consider 1 terminal state, and that's easier to reason about. So those 2 states are actually the same state. Next is the set of finite actions. In this grid world, we have 4 actions. We can go left, right, up, or down. Next is the transition probability function. It tells us if we're in state S and we take action A, what's the likelihood that we end up in state S prime? So in our example, it's quite simple. Consider state 5. So if we're in state 5 and we take action up, we end up in state 1 with 100% probability. If we're in state 3 and we take the action right, we end up back in state 3 with 100% probability. And if we're in the terminal state, whatever action we take, we're going to end up back in the terminal state. Next is the reward function. This tells us how much reward we expect to get when we take action A in state S. And reward is good when it's positive, and we generally want to maximize reward. In our example, reward is always -1 for any action taken, except in a terminal state, in which case the reward is always 0. Next is the discount factor gamma. So in an MDP, what we want to maximize is a return G, which is all future rewards scaled by gamma. So we have reward at t plus 1 plus gamma times reward at t plus 2 plus gamma squared times reward at t plus 3, and so on. So you can see that if the discount factor is small, then we care about short-term rewards, and if the discount factor is large, then we care about long-term rewards. And you might ask, why not just always set discount factor to 1 so that we care about long-term rewards? One reason is because we're not 100% sure that the MDP accurately represents the environment. So this uncertainty just drives us to take some short-term rewards when we can. So we're not always going to set gamma to be 1. Now we're going to discuss the value functions, but first we have to explain what a policy is. A policy is a mapping between states to actions, so it tells us at state S what action we're going to take. On the bottom right, we have an example policy for the grid world. It's a pretty simple policy, it just points us towards the terminal states. And again, I have the return listed here. It's the all future rewards scaled by the discount factor. So there are two value functions we're going to consider. The first one is a state value function. So under some policy pi, what's the expected return we get if we start in state S? So if we consider a discount factor of 1 in our example policy, at state 1, the value is -1 because if we take the action left, we get a reward of -1 and it brings us to the terminal state. The value at state 3 is -3 because it takes us 3 steps to get to the terminal state if we take the left action 3 times. So the next value function is the action value function. It tells us if we're in state S and we take action A, what's the expected return we get under some policy pi. So in our example, if we're in state 3, we take action left, we get a value of -3 because we get a reward of -1 by traveling to state 2, and then the value of state 2 is just -2. And if we're in state 3 and we take the action right, then the action value is -4 because we get a reward of -1 and it brings us back to state 3, and the value of state 3 is -3. So in any MDP, there's some optimal policy pi star. And the way we define this optimal policy is just for any state S, the value of this state under our policy pi is greater than or equal to the value of that state under any other policy. We can also define the optimal state value function and the optimal action value function. So the optimal state value function is just the value of each state under some optimal policy. And of course we can use V star as this optimal policy. In general, there can be many optimal policies. In our grid world example, the bottom right is an optimal policy, but we can see there's some flexibility in states 9 and 6. So I could say in state 9, go left, and that'd still be optimal. Now we're going to go over how to find the optimal state value function. One way is a value iteration algorithm, and this derives from the Bellman expectation equation. The Bellman expectation equation just tells us that the value of state S under some policy pi is just the expected reward at the next time step plus gamma times the value of the state we end up in. Why is this true? Well, let's consider the definition of the value function. So it tells us what it is the expected return given that we start in state S under some policy pi, and we can expand this. And if we factor out gamma, you can see we have just gamma times the value of the next state. And value iteration is described in the equation on the bottom left. So consider state S. We are updating its value to the value we get when we choose the best action. So when we choose the best action, we get some reward and some value at the next state, and we add those together, and that's what we update the value at state S to be. And let's go over an example. So on the right hand side, consider the square in blue. So first we initialize all state values to 0, and let's go over this first iteration here. So we have to choose the action that maximizes the reward plus the value at the next state. And also we're just considering this count factor to be 1 for simplicity here. So at this first time step, it doesn't really matter what action we take. We always get a reward of -1, and the value of the next state is going to be 0. So we update this state to be -1. The next time step is similar. No matter what action we take, we end up in a state that has value -1. So let's just consider taking action up. We get a reward of -1, and the value of the state we end up in is -1, so we just update this to -2. For the next iteration, if we take action right, we end up in a state that has a value of -2, but if we take action up, we get a better value of -1. So we're going to pick action up or left. So we get -1 plus -1, and this remains -2. So this will eventually converge to V star, and this happens at time step 7 in our example. So this should make sense why the value of each state is just the number of actions it needs to take to get to the terminal state. Then after we have the optimal value function, we can easily get some optimal policy. So for each state, we just consider all the actions and we pick the one that gets us the greatest return. So this would give us a policy that just points towards the terminal state. So what if we don't know the transition and reward function? Well, this is called model free, and we can't use value iteration because this depended on knowing the transition and reward function. If we just go back, you can see the reward function here and the transition probability function here. So we don't know that anymore. So can we still learn the optimal value function? Well, yes, we can, and we're going to use the Sarsa algorithm. So we're actually going to learn the optimal action value function in this case. The key step is highlighted in red. This is the update we're going to apply. So it's the reward plus discount factor times the action value function that we get at the next time step minus what we predicted this action value function to be. And this makes sense because the reward plus gamma times the action value function, this is going to be a better estimation than what we previously had because we actually see a reward R. So let's go over this algorithm. We first initialize the action value functions for all states and actions. So it actually doesn't matter what we initialize it to, and then we set the action value function at the terminal state to be 0. And then what we do is we start with the state S and we choose A from S using policy derived from Q. So this is just going to be, we're going to pick the best action, and it says epsilon greedy. This just means with probability epsilon we choose some random action just for exploration, and this is important to ensure that this algorithm actually converges. So we're going to take action A, observe reward R, and S prime the state we end up in, and we're going to apply this update as described before, and we just repeat this until the action value function converges, and this is going to be the optimal action value function. We can even learn the optimal action value function in an off policy setting. So off policy means we can learn from episodes generated with a different policy. So this is kind of the idea of, if I use an analogy, we can learn from other people by watching what they do. If they make a mistake, we know not to replicate the mistake, and if they do something good, we know to emulate their actions. So the crucial difference between this and SARSA is we choose the max A prime instead of the action that would be generated under that different policy. And this algorithm is called Q-learning. So we see a state action reward and the next state, and again, instead of considering the next action that's actually taken, we just consider the best action according to our state value function. And this is going to tell us eventually it's going to converge to the optimal state value function. And the algorithm is very similar, so I won't go over it. So the previous methods are a good way to get the optimal value functions, but they're pretty resource intensive. You can just imagine just storing them would take O of S memory. So this would not be possible for problems with a large state space such as Go, the board game Go, which has 10 to 170 states. And in some robotics applications, there's a continuous state space. So what we do is we're going to use neural networks to approximate the value functions. And theta, the parameters, are what we store instead of like a lookup table that tells us the value at each state. So one of the algorithms that does this is DeepQ Networks. So what we do is we're going to store state action reward next state tuples in a replay memory D, and the loss is going to be, it's similar to the loss in Q-learning. It's reward plus gamma times the action value function under the best action minus what we predicted this action value function to be, and we're just gonna back propagate on this loss, and we're gonna sample batches of transitions from this replay memory D. This is the algorithm that was used in the famous paper to play Atari games. In this case, they use the CNN to approximate the action value function. And here's the algorithm listed if you want to review it. So in conclusion, again, this was just a brief overview of reinforcement learning and how neural networks play a part in it. So if you want to learn more, you can check out the resources linked here. And I hope you enjoy this course and have a good winter break.